Hello students, today we are going to start a new chapter, that is oscillations. In this chapter, first we will understand what is the periodic motion and oscillatory motion, what is the difference between periodic motion, oscillatory motion and SHM, that is simple harmonic motion. Then we will revise the concept of period and frequency. Then we'll see the displacement in oscillatory motion, the simple harmonic motion, which motions are considered to be simple harmonic motion, the condition for a motion to be simple harmonic motion, etc. Then we will see the SHM and the uniform circular motion, the relation between SHM and uniform circular motion. After seeing the displacement in SHM, we'll see velocity and acceleration in simple harmonic motion as a function of time and as a function of position. Then we will see the energies which are consumed in the harmonic motion, that is potential energy and kinetic energy. Then we will see some systems which are executing SHM, that will include the simple pendulum, the spring block system, the physical pendulum, the U-tube, etc. Then we will see the two types of oscillation, that are damped oscillation and undamped oscillation. The damped oscillations are the practical oscillations, includes all the resistive forces. And then the types of damped oscillation, that will be forced oscillation and resonance condition. So now let us begin. Let us first understand the periodic motion, oscillatory motion and SHM and the difference between them. First, let us see the periodic motion. Say for example, an object is moving in uniform circular motion. It is moving in uniform circular motion. Now, it will take some time to complete this circle. After completing circle, it will again be at its initial position. Again, it will continue to move on same path. So, after certain period of time, this particle will repeat its motion. Let us see another example. We have kept two wedges. One ball is rolled from the top of one wedge. This will further come down. It will lose its potential energy, gain kinetic energy, so it will roll up the wedge. And it will continue to move as we ignore the resistive forces. So after certain period of time, it is also repeating its motion. We can also take the example of pendulum. That is also making periodic motion because it is repeating its motion after certain period of time. So the meaning of periodic motion is, if any object repeats its motion after certain period of time, then it is said to be periodic motion. Now, what is oscillatory motion? Most of the students are always considering periodic motion and oscillatory motion are to be same. But let us see. The motion of pendulum is called oscillatory motion. This is the mean position of pendulum. It will make to and fro motions about the mean position. So it is oscillatory motion. Remember, all oscillatory motions are periodic, but all periodic need not to be oscillatory motions. So the oscillatory motion is the to and fro motion about mean position. Is called oscillatory motion. Here, important thing to note, all oscillatory motions are periodic, but all periodic need not be oscillatory. Now, the third type, SHM. SHM is the oscillatory motion for small displacement. The SHM stands for simple harmonic motion. What is simple harmonic motion? That will understand detail in next lecture. But let us just write down the condition. If acceleration of any particle at any point follows this equation, a is equals to minus omega square x, where a is the instantaneous acceleration, x is the position, and omega is the angular frequency, then that motion is said to be simple harmonic motion. It is basically an oscillatory motion with small displacement. So again, we can say that all SHM are oscillatory and all oscillatory are periodic. So all SHM are oscillatory and they are periodic. But all periodic are not oscillatory and all oscillatory are not SHM. So let us write down all SHM are oscillatory, but all oscillatory motions are not SHM. So in general, we can write the note that all SHM are oscillatory and all oscillatory are periodic, but the reverse need not be true. Now let us revise the concept of frequency and time period. The time period it is the smallest amount of time in which motion is repeated. The SI unit of time period is second, and the frequency is the number of oscillations that takes place in 1 second. The frequency is denoted by F or sometimes it is denoted by nu, that is equals to 1 by time period t. The SI unit of frequency is hertz. One hertz is equals to 1 second inverse. Now let us understand what is displacement. Till now we just understand about displacement as a change in position with respect to the origin or with respect to the reference point, but it is not always related to position. The displacement in general refers to the change with time of any physical property under consideration. For example, in case of a rectilinear motion of ball on surface, the distance from starting point as a function of time is position displacement. The choice of origin is matter of convenience. If we consider a pendulum, then this is its mean position. If we take mean position as a reference, then this will be its displacement. Same way, if we consider a spring block system, then we take its equilibrium position to be mean position, and if we stretch or compress, the displacement will take place. But we have to understand here that the term displacement is not always to be referred in the context of position only. There can be other kinds of displacement variables. For example, the voltage across a capacitor changing with time in AC circuit, the pressure variations in time with the propagation of sound wave, the changing electric and magnetic fields in a light wave. All these are displacement variables. The displacement variable may take both positive and negative values. The displacement can be represented as a mathematical function of time. In case of periodic motion, this displacement function is periodic with time. Let us see an example. There are two graphs for two different waves, wave A and wave B. The position time graph is given. We want to find the time period and frequency of A and B. Here, the time period is the time after which the motion repeats itself. First, let's say for A, it starts from mean position, it increases, then again at mean position. After that, it moves in negative direction and again mean position. Then it will repeat itself. Here at 0.5 second, we cannot say it is repeating itself because it is moving in negative. Now after this point at 1 second, it is again repeating the same type of motion. So time period for A will be equal to 1 second. Same way if we see for B, it is repeating its motion after 0.5 second. So time period for B will be equal to 2 seconds. Now the frequency of E is 1 upon time period, that is equal to 1 hertz, and frequency of B, that is 1 upon time period of B, the time period of B is 0.5 second. So 1 divided by 0.5, so FB will be equal to 2 hertz. Now let us see how oscillatory function is represented as a sinusoidal wave. Sinusoidal wave means as a sine function or cosine function. So let us consider a pendulum which is oscillating about its mean position. Let's say this is the maximum displacement in either side. This is mean position, x is equals to 0. Let's say this is displacement, x is equals to plus a, and this is x is equals to minus a. We have taken this direction to be positive and this direction to be negative. Now at t is equals to 0, it will be at this point. After some time it will be at point x is equals to a. Then from this it will again pass mean position, move towards the x is equals to minus a position, and again it will move to mean position. This whole journey is considered to be one oscillation. Now if we draw the displacement versus distance graph, if the oscillation is starting from mean position, initial displacement and distance will be 0. Now it is moving gradually towards the extreme point A. So its distance and displacement both are increasing, but it is not increasing linearly because the acceleration is not constant. So the displacement is also increasing and distance is also increasing. This is maximum displacement. Let's say this is A. After reaching to point A, it will again come to mean position, x is equals to 0. But as we know, distance is always added, displacement will decrease, but distance will increase. So displacement will decrease, it will again reach to mean position, that is x is equals to 0, but distance is increasing. Now after that it will move towards x is equals to minus a. As it is moving in opposite direction, we will take this in negative. So it will move in the opposite direction, x is equals to minus a. Again, even if it is moving in opposite direction, the distance is always added, so distance is increased. From this it also again comes to point mean position, that is displacement will decrease but distance still will increase. So this is one oscillation. Now if we put time instead of the distance on x-axis, then also graph will be same. If we have taken distance on the x-axis, then the distance traveled by oscillating wave in one oscillation is called one wavelength. So this much distance will be wavelength lambda. Now if we have taken the time on the x-axis, then the time taken to complete one oscillation is called time period, capital T. If this whole much distance is lambda, then half will be lambda by 2. This will be lambda by 2, and the 1/4 will be lambda by 4. Same way, this half will be t by 2 and this will be t by 4 time. As we have taken distance and time on the x-axis, we can draw the sine function as a function of angle. we know different values of angle, that is 0, 30 degree, 45 degree, 90 degree. So for simplicity we'll make it 0, 90, 180, 270 and 360 degree. We know the value of sine 0 is 0. Sine 90 is 1. It is not a linear function. Sine 180 is 0 again. Sine 270 is -1. And sine 360 is again 0. So if we see these two graphs, they both are same. So we can say that we can represent the oscillatory motion as a function of sine or cosine wave. So from these two graphs, we can say that the displacement time for a pendulum can be represented by the sine function. So x of t, that is position of pendulum bob at any time instant t, is equals to a sine of omega t. Here omega is the angular frequency, which is equal to 2 pi by t. Here t is the time period. Now let us understand the unitary relation between wavelength, time period and angle. For given oscillatory motion, we can draw the displacement versus distance graph, displacement versus time graph, and displacement versus angle graph. If it is distance on x-axis, the distance between these 2 points will be one wavelength lambda. If there is time on x-axis, then the distance between these two will be one time period t. And if it is an angle, then the total angle will be 2 pi. Now let us consider 2 points having some path difference between them as delta x. So we want to find the phase difference, that is angle difference, and the time gap between 2 points 1 and 2. So let us first find the path difference. For the path difference of lambda, the phase difference is 2 pi. Then what will be the phase difference for the path difference delta x? So we can write it in unitary method. For path difference lambda, the phase difference is 2 pi. So what will be the phase difference for path difference delta x? So phase difference delta phi will be equal to delta x into 2 pi by lambda. Same way we can write for path difference lambda, the time gap is capital T. So what will be the time gap if path difference is delta x? So for path difference lambda, the time gap is capital T. Then for delta x, the time gap will be delta x into t by lambda. So like this, if we know one difference between 2 points, that is either path difference, time gap or the phase difference, we can find the other two differences. So you must understand and remember this unitary relation between angle, distance and time. Now let us see one example. In this, a graph of displacement versus time is given for a wave having wavelength 2 mm. The time period from this we can see it is 4 seconds. There are 2 points on the graph A and B. We want to find the phase difference, path difference and time gap between A and B. Here if we write angles, then this angle will be 0, this will be pi by 2, this will be pi, this will be 3 pi by 2 and this will be 2 pi. So clearly the phase difference between A and B is pi by 2. So delta phi will be equal to pi minus pi by 2, that is equals to pi by 2. Now we want to find the path difference and the time gap. So for the angle of 2 pi, the time gap is 4 seconds. Then what will be the time gap for the angle pi by 2? So delta t will be pi by 2 into 4 divided by 2 pi. This pi will get cancelled out. So delta t will be equal to 1 second. Now the path difference for, let's say, time gap 4 seconds, the path difference is 2 mm. Then for time gap 1 second, the path difference delta x will be 2 mm into 1 divided by 4. So delta x will be equal to 0.5 mm. In this example, we want to check whether given functions are periodic or not, and if they are periodic, we have to find their periods. The first function is given as sin omega t minus cos omega t. Here sin omega t and cos omega t are individually periodic function. Whenever two individually periodic functions are added or subtracted, in general we can say it is added, then the resultant will also be periodic function. So let us write down when two or more periodic functions are combined, that is, they are added or subtracted, then the resultant function will also be periodic. So this function is periodic. If it is periodic, then we have to find the time period of this function. The sin omega t minus cos omega t can be written as root 2 into 1 by root 2 sin omega t minus 1 by root 2 cos omega t. We have multiplied and divided with root 2. So root 2 can be written as sin omega t sin pi by 4 minus cos pi by 4 cos omega t. So this can be written as root 2 into sine of omega t minus pi by 4. So here the multiplicand of the time is omega. So angular frequency will be omega only, and it is given by 2 pi by t. So time period will be 2 pi by omega. Here we should note that when two functions having same angular frequency are added or combined, then the resultant angular frequency will also be same and resultant time period will also be same. Here pi by 4 is the phase difference. We will understand after this example what is phase difference. The second function is log 2 omega t. If we draw the graph of log function, then it will be somewhat like this. It is not a periodic function. The logarithmic function and the exponential functions are not periodic. So, note it is non-periodic. Let us note all logarithmic and exponential functions are non-periodic. In the third example, the function is given as cos omega t plus sin 2 omega t plus cos 4 omega t. Here we know that these individual functions are periodic, so their addition will also be periodic. So the function is periodic. Now we want to find the time period of the whole function. For that, first of all, we will find the time period of individual function. Let's say time period of this is t1, for this it is t2, and for this it is t3. So omega is the angular frequency, so omega can be written as 2 pi by t1. So t1 will be 2 pi by omega. Same way, t2 will be 2 pi by 2 omega, and t3 will be 2 pi by 4 omega. So here the largest time period will be the common time period for the whole function. So time period of the function will be 2 pi by omega. Why is it so? Let us understand from the waveform. This is a function having time period t1, that is equals to 2 pi by omega. The another function has time period t2. We can write t2 is equals to t1 by 2. That is, its time period is half. So its waveform will be like this. The third function, it has time period t3 is equals to t1 by 4. So it will be half of this. We can see after time period capital T only, after time period 2 pi by omega only, the whole pattern is repeating. So we can say the time period is 2 pi by omega. So in this kind of cases, always take the time period which is the largest. So here t is equals to 2 pi by omega will be our answer. Now let us understand what is the phase difference. In the graph of sinusoidal wave representing the oscillatory motion, we have seen graph for a motion that starts with mean position x is equals to 0. But it is not necessary that the oscillatory motion always starts from x is equals to 0. It can start from any point from this path. So in that case, what will be the graph? Let us see. First, if we draw the graph for which it is starting from mean position, then the graph will be like this. This angle will be 0. This is pi. And this is 2 pi. Now, let's say if it starts from extreme position, then at t is equals to 0, this is time, at t is equals to 0, the position will be maximum position. After t by 4 time, so this will be the graph of one complete oscillation. If we see, this is the graph of cosine function. So we can write this graph as sine of omega t plus pi by 2. This graph was sine of omega t. So the difference, the phase difference between these two graphs is angle pi by 2. This is cos pi by 2. So in such case where the oscillation does not start with mean position, we will have some angle added with this omega t. This angle is called the phase difference or initial phase. So sine omega t plus phi, where phi is the initial phase. The initial phase will give us the point from which the oscillation starts. Say for example, if it is given that sine of omega t plus pi by 4, this is the initial phase pi by 4. We want to find the starting point from which the graph starts. So x of t is equals to a sine of omega t plus pi by 4. The initial position, that means at t is equals to 0. X of t will be equal to a sine of 0 plus pi by 4. Sine pi by 4 is 1 by root 2. So x of t will be equal to a by root 2. So if initial phase is pi by 4, then oscillation will start from point a by root 2. Now, if we want to start from x is equals to a by 2, then what should be the phase difference? The function is given by x of t is equals to a sine of omega t plus phi. We want x of t to be a by 2 is equals to a sine of initial phase, that means t will be equal to 0. So 0 plus phi, that will be phi. So 1 by 2 will be equal to sine phi. So phi will be equal to pi by 6. So the initial phase will be pi by 6. So the function can be written as x of t is equals to a sine of omega t plus pi by 6. So basically initial phase will give the point from where the oscillation starts.